Hello, my name is Sterling, and today we're going to be solving a strain gauge data question. As you see in our figure, we have our strain in A, B, and C, all separated by 60 degrees, and the given values are as listed. And the material that's being tested by the strain Rosette is AISI 302 steel with Young's modulus of 28,000 KSI, Poisson's ratio of 0.27, and a shearing modulus of 10,800 KSI. So here our problem statement wants us to find the principal stress in this material. So in order to do that, then we have this flow chart. So from our given strain gauge data, then we will use the strain Rosette equations to find our state of strain, and then either use generalized Hooke's law to find a state of stress, and then use Mohr's circle to find our principal stresses, or after you have your strain Rosette equations and get your state of strain, you can use Mohr's circle to find your principal strain, and then use generalized Hooke's law to find your principal stresses. Today we're going to be going this left route, just because it works better for me. And we'll start by using our strain Rosette equations right here. So we have our epsilon A, epsilon B, and epsilon C, but we don't have our thetas. So looking at this figure, we can say that theta A is 0 degrees from the x-axis. Theta B is negative 60 degrees, and theta C will be negative 120 degrees. So now we'll plug in epsilon A and theta A into this equation, and that will yield epsilon x to be 475 times 10 to the negative 6. That is because if you plug in 0 for theta A, then this becomes 0, this becomes 0, and this term right here equals 1. So cool, we'll call this equation 1. Now we're going to do the same thing for epsilon B, and plugging in negative 60 for theta B in here, then that epsilon B into this equation, that yields epsilon y 1.08 times 10 to the negative 4 plus 0.577 gamma xy. Gamma xy is our shear strain. So we'll call this equation 2. And this was taken just from plugging in your epsilon B and theta B into this equation, which yields what we see here. Now we'll do it for the third equation, same process, plugging in epsilon C and theta C into this equation, which ends up yielding gamma xy to be negative 5.20 times 10 to the negative 4th. We'll call this equation 3. So now we have 3 equations, and this is known now, so only 2 unknowns. We'll plug in equation 2 into equation 3. Sorry, you didn't see that. So we'll do equation 2 into equation 3. That yields epsilon y to be negative 1.92 times 10 to the negative 4. Awesome. So now we have our epsilon y, our epsilon x as well as our shear strain. Now we are going to use generalized Hooke's law to find our this should be x and this should be y. So now, like I said earlier, we have our state of strain now. Now we're going to use generalized Hooke's law to get our state of stress, which can be seen using these equations. So sigma x is going to be our Young's modulus, our modulus of elasticity, which is 2800 over 1 minus Poisson's ratio, which is from up here 0.27 squared, parentheses, epsilon x plus Poisson's ratio times epsilon y, which will come out to be 4.75 times 10 to the negative 4th times 0.27 times negative 1.92 times 10 to the negative 4th. So if you do this math, our state of stress for x equals 12.8. Now, we do the same thing. These should also be like that. Now for solving for our state of stress for the y direction, it'll be, let's see, y equals 20,000 1 minus 0.27 squared times negative 1.92 times 10 to the negative 4th. Sorry, this is a plus, by the way. Plus 0.27 times epsilon x, 475 times 10 to the negative 6. And this yields negative 1.93. Looking at our generalized Hooke's law equations, we want to find, oh man, I'm all messed up today. This is supposed to be tau xy, which is our, our shear stress, which is found by multiplying the shear strain times the shearing modulus. So to do that, equals gamma xy, which is up here, negative 5.20 times 10 to the negative 4th, times the shearing modulus, which we found earlier out of the property tables to be 10,800 KSI. Therefore, our shear stress equals negative 5.62. So now that we have these three numbers, those are our states of stress. So now we can use Mohr's circle to find our principal stresses, which the problem statement was asking for. So now we're going to graph our points on Mohr's circle. Let's see how good I can draw today. This is sigma and tau. So the way that we graph this is the points that are plotted are so the points that we want to plot are our state of stress for y, comma negative tau xy, and our state of stress for x, comma tau xy. So we'll go ahead and write in, here was negative 1.93, that's our sigma y, as, get my paper, right here, there's the negative 1.93, and then 12.8 we'll say is about here-ish. And then tau xy, we'll put that here, at negative 5.62, and up here, 5.62. So then if we're graphing this, sigma x, comma tau xy, since tau xy is already negative, a negative of the negative will be positive. Sorry, that was wrong. It's positive tau xy, which means it's negative 5.62. So that's here. And then sigma y is negative 1.93, comma negative tau xy. Negative tau xy ends up being 5.62 and positive. We also want to find, get this out of the way, sigma average, which is tau x plus tau y over 2. And in this case, plugging in 12.8 for sigma x, negative 1.93 for sigma y. Then our our sigma average ends up being 5.435. So that'll be in the middle. And we draw the diameter here. Now the hard part, make a circle. Man, I messed that up so bad. So something more like that. Now, if we want to find our maximum shear stress, that is going to be this, which is R from here to here. Because then if this is rotated completely vertical or, all the way up or facing all the way down, that'll give us our maximum tau xy value. So Mohr's circle is a really easy and mathematically correct way to find principal stresses. That's relatively easy. So to find R, it's going to be pretty much Pythagorean theorem. So we have this distance right here, squared plus 5.62, which is this distance squared, and we take the square root of that. So 5.62 squared plus, and then we do 12.8 minus 5.435, which ends up being 7.362, I believe. And that ends up making R to be 9.26 KSI. Now, if we want to find our max strain, it's going to be our average plus our R value. So our max principal stress will be 5.435 plus 9.26. That yields, 14.70 KSI. For the min, it's same thing, but you're subtracting R. So 5.435 minus 9.26. So our minimum stress is going to be negative 3.83 KSI. Double check to make sure that's right. Yep. And like I said earlier, our R value ends up being our max shearing force. So that is 9.26 KSI. And there's our answer using Mohr's circle and the generalized Hooke's law after the given strain rosette that we have. We're able to calculate and find principal stresses right here. And for verification purposes, there's my signature. Here's my face. Thank you.